And in that vein, first of all, I kind of reorganized the project tabs a little bit. So now if you look on the side here, you'll see that there's a tab for final project. Okay, if I click on that, I'm going to get everything I basically need to work on the final project. The updated version of the instructions for the project, description of what it is and how it's going to be done. The data set, notice I've deleted the 2011 data set. There's only the 2014 data set because we're going to be working with that. Two reasons. One reason is that if we go down further here, I've given you some examples of previous projects that were done using the 2011 data set. So I want to make sure that you have a chance to work with a separate data set. And you can take a look at these. I'm going to open one up here. Okay, just so we can take a look at it. So this person put together basically an introduction, as we describe in what we ask you to do, and it's background information. She did a little bit of research. Okay, and I think she actually, this one she only has one. I think she only has one reference on here, but you may want to, add some additional references as well. And this is exactly the way she formatted it to display on the board. In other words, she printed out each one of these out as a page. Notice the text is very large because when you're presenting it on a board as a poster, you want someone to be able to stand a few feet away and be able to read the thing, right? So the text size is big enough. Now, you can submit the same thing that you put on the poster board as your final project, upload it if it's a PDF file or a PowerPoint file or something like that. It appears to me she used PowerPoint because rather than Word or something like that. And PowerPoint's pretty good for this because it makes it easier for you to copy and paste in images. It's almost like a page layout program. It's easy. It's a lot easier for you to put side by side graphs and text boxes right under them and move it around and stuff in PowerPoint if you've worked with it than it is with Word. But you can do it any way that you want. Okay, you can even, if you want, print it out, paste it up, and scan it, into a PDF file or something like that. If you really feel uncomfortable using computers. But basically, she started with an introduction and she did a little bit of reference work. I would have liked another maybe reference or two. Not like I said, not like Time Magazine, some technical reference. In this case, it was a study. It was information from Morbidity and Mortality Weekly Report. And she did. I'm sure she used some other references as well for what she tells us about influenza and the immunization and so on and so forth. And she talked about how our methods, where the data came from, how it was collected, so on and so forth. She gave us some descriptive statistics. She calls it demographics, right? But same thing, descriptive statistics. It gives us basic idea of how many people took place in this study, how many of them were male, how many of them were female, what age ranges were they in, and this all came from. Don't look at me. Look at that. Oh, you are looking at that, right? Okay, good. Okay, so this all came from where? It came from the Community Health Survey. She got it right from the survey. And she organized this data this way. And then she was able to, with the data that she had in SPSS, she was able to produce a histogram of the age distribution. She was able to give us a age distribution by gender. And if you notice, that's kind of interesting what she did there. Look at the female population. The female population is older than the male population. In other words, here, like over here, look how many more females there are in this population than males. If you look down here, 18 to 29, difference is not that big. But as they get older, there's a lot more older females in the population. They're susceptible to cancer, heart disease, so on and so forth. And then she went on to compare some of the different parameters that she wanted to, some of the different statistics she wanted to compare in terms of why would a person get immunization or not. For instance, maybe health insurance has something to do with it. Maybe sex has something to do with it. Maybe nativity, born in the United States, not born in, maybe that has something to do with it. She compared those. Then she did statistical tests that were associated with them to see if she could prove statistically that there's a difference between gender, whether a gender would influence your getting a flu shot, and so on and so forth. And she summarized all that data, and then finally she gave us a conclusion. Okay, I love this one because I don't have to spend days trying to read it. It's not 8,000 pages long. It's easy to text to read. It's large text. If it was on display, I'd be able to understand what was going on and the information she's trying to convey in this very easily and very quickly. Okay, now I don't want you to copy this. I want you to do your own work. Certainly you're going to have to, because it's going to be a different database. So you're not going to be able to use her numbers for sure. But this will give you kind of a guideline. And I'm not even sure you necessarily have to look at exactly the same statistics. In other words, you might want to look at whether or not, within reason. I'm gonna give you kind of a preposterous example. What's the likelihood of is it people that drink a lot of sugary drinks, are they more likely to get a flu shot than people that don't drink a lot of sugary drinks? Well, gee, that's interesting, but it's pretty useless, right? So I wouldn't expect you to use, but you have almost 200 other variables, 200 other questions that were asked. Maybe you can find something on there beyond the few that we mentioned in other words, you should do the ones that we mentioned for the different choices. But if you want to do another one, you see something else that's of interest, certainly it would be nice to see you do that. And then finally, she wrote up a concise discussion and conclusion. Okay, and you'll see similarly with another one. And you can take a look at these on your own. They're all different ones. This one, I think Pearson used their own data. That last one, avian. Let me open this one. Okay, sugary. Oh, look, sugar. Okay, funny. I should mention that. Obesity, sugary. Now, remember, the topics might have been different than the ones that you have for this semester. So this one involved obesity and sugary drink consumption. Okay, so and if you want to get creative, if you don't want to do one of the three topics we suggested with the variables we suggested, you can certainly, upload that. I would have liked to have that a little sooner, but you certainly have time to do that still. And again, an introduction, some references, our descriptive statistics tells us about the population, tells us about the variables that she's examining, how many males, how many females, the employment status, the ethnicity, tells us the method she uses, her results, her statistical results. She summarizes them graphically, and she gave me a nice summary and conclusion. Again, something that you could easily post onto print out and then put onto a poster board so that you could read the thing efficiently. Okay, so why are these up here? Because they're among the better ones that we saw. Does yours have to be as elaborate or as ambitious as some of these? No, absolutely not. But this will give you an idea of kind of what we're after. So you got 4 of them there, and the more creative and the more challenging you want to be, that's fine with you guys. But use this kind of as a guide, for what the format of this thing should be. Now, again, I said she, I don't know who it is, he also formatted this for his presentation, and he used the same file, whether it's a PowerPoint or a PDF file. He used the same file to upload for his grade when he was done with the work. In other words, as his paper. Right? You don't have to do that. You can have one version for your PowerPoint, which is formatted well for that. And if you want to do it a little bit differently for what you upload, you can do that also. Okay? So does that make sense to you guys? You guys comfortable with that? I don't see any tears. I don't see any enormous shock. I see a little worry, maybe, a little concern, but I think that's as bad as I see. That's good. A little concern is okay. Panic is not good. Right. Okay. So really, look at this. It's 7 or 8 pages long. It's not a thesis. Don't go nuts. Right. I'm more concerned about you demonstrating you understand this idea of doing a little bit of background research and presenting it, giving me a little bit of background. understanding what descriptive statistics are, finding an efficient way to communicate them, with tables or graphs, using the right analysis method to analyze whether or not these variables that you're comparing, these influences that you're looking for, these hypotheses that you're testing, to tell me whether or not they're statistically significant, and what the p value or significance is, and so on and so forth. What test you're using, odds ratio might be nice. If it's the type of analysis that demands an odds ratio. You might, if it's not, then you wouldn't have that. Okay, and then summarizing your results and your conclusions for me, concisely. Okay, so that's really what we're after, and I got a feeling you guys do okay. Now, the next thing in this tab, okay, under this tab, under the project, we had our document, which summarizes what we need to do, our data, which is New York City Community Health Survey 2014. We have 3 steps into participating in this. Actually, I didn't make that available because it's not relevant to the way I set the tabs up. So ignore that. That shows up on mine, not on yours. Some example projects. And then I put up I'll come to this in a second. You won't see these on yours either. Okay, so the next tab that you see here, beyond final project, is you see final project selection. I won't click into that. Some of you have already uploaded information to that. That's where you told me which of the 3, or if you were doing something that didn't involve those variables and you wanted to branch off into something else, that's the place where you had the opportunity to tell me about that. Next is project date selection. And you can click into there, and this is what you call a wiki. Okay, now I put a wiki up before, and you guys, this time you got the right idea. Okay, the last time I put a wiki up, you added comments to it instead of actually changing the document itself, right? So this time we got the right. I communicated it a little bit better, I think, this time. So we have people signing up for Monday and Wednesday. There's no limit on. It's nice that night. It would be beautiful to get them equal numbers on each night, but that's not necessary. Okay. If we get more people on Monday night, that's okay. We'll have plenty of time. If we keep it to 5 or 6 minutes per person, we'll have plenty of time. So I anticipate that everybody will be able to choose the night they want to present. If you present on Monday, you don't have to come on Wednesday. If you present on Wednesday, you don't have to come on Monday. However, if you're presenting on Wednesday, maybe it would be nice to come on Monday, to support your fellow students, and also to get kind of a leg up on, gee, what's going on here? What are these people doing? Right? That wouldn't hurt. Now on Wednesday, similarly, if you had some odds and ends or something like that, or homework you had to complete, if we have a little bit of time, I can sit with you. Okay. Now the thing is, you have to upload. So if you present on Monday night, you have to upload your final document by the end of that night, midnight or something like that. Okay, so that I can start grading them. They give me a very little short window in the summertime to get the grades in before they lock everything out. And it becomes a hassle because then I have to write up a whole form to do it individual grades. That's terrible. Trust me, I don't want to do that. So I have a very short window. So particularly on Wednesday, make sure you upload your work by the time Wednesday night comes. Okay, so that's where that is. So I see people are already signing up. So we have that added away. And then over here, if we go down to project submissions. So now in here, you have a place where you could upload your introduction and your descriptive statistics, right? Then you have a place where you can upload your statistical analyses, your methods that you used, and so on and so forth. And finally, you have a place where you can put your final submission. Okay, now I put due dates of 7/18 on first project submission, and 7/22 or 25 for the second project submission, and they're soft due dates. I just put them down to encourage you to do it before you have to present. Okay, so when I say 7/22 or 7/25, if you're presenting on Monday, try and get it in by 7/22. If you're presenting on Wednesday, try and get it in by 7/25. And why am I doing that? I'm doing that so I can glance at it And if you're way off base or you went off the rails somewhere, I can respond to it, and you have at least a little bit of time to kind of go back and maybe fix things and so on. So it'll help you out a little bit if you if the sooner you get it in, the better. So it'll give me a chance to look, glance at it. And I can't promise I'm going to really examine them carefully, but I'll at least take a quick look. Okay, especially if you're concerned and you email me, then I'll make sure to take a look at yours. So that's what I'm doing there. Is I want you to submit it in stages so that if you're concerned and you need me to look at it, I can do that. And then the final project submission again is based on the date. It's the same as the date that you've given your presentation. Okay, so, and I think that's it, right? It's not that threatening. It's not a thesis, right? And I think you have a pretty good idea what you're going to need to do. Any questions among you guys here that are in here? Is that pretty clear for you guys? We're okay. We're not panicky. We're okay that we'll be able to figure this stuff out. How about you guys in the peanut gallery online? Okay, let me look back here. There are a few questions. Okay. These are 2 independent variables. She has 2 independent variables, but I have just 1. Georgie, I'll tell you what, email me. I'm not sure what you're referring to, but email me. We'll figure it out. Do we have to make all our tables and graphs in Excel? Somebody just brought that up in here. I didn't even realize that until they brought it up in here. The people on these particular examples seem to have used Excel quite broadly for their graphs and their tables. And I think it's even possible they either copied the data in off SPSS results or even retyped them or whatever, right? And I think they did that because they felt they had more control over the tables and graphs. It makes it nice and pretty. They were able to, if you're have a lot of facility with Excel, you can get pretty fancy with the graphs and so on. But that's not needed. In other words, you can use the graphs and the tables as they are produced in SPSS, but you can also, if you want to make it a little bit more fancy, or you think you can clarify it a little bit better, you can use Excel, right? So it's not, even though for some reason or other I wound up with examples that seem to have been produced in SPSS, in the Excel. Actually, I think some of them, I'm sure that histogram was not done. Yeah, I don't think that histogram was done in Excel. She found a way to edit it and color it in SPSS. So if you double click into the charts and tables, it is possible to edit them, but make things bold, change colors, and so on and so forth. So you guys can experiment with that. I'll try and be as impartial as possible and not be swayed by a person's artistic ability. As best I can, since this is a statistics course, right? But like I said, you can use Excel or SPSS, or even if at work you've been using SAS or some other program or R, for instance, and you have some experience with that, and you want to use that, I'm perfectly okay with you finding any method you want to use these. There's some online generators for charts and tables. Yes.
How strict you're going to be with citations and the format APA?
No, absolutely not. Don't worry about it. Okay. You can be. I'm not. The question was, how strict am I going to be on the formatting for the references?
Yeah.
Which is American Public Health Association, American Psychiatric Association. They all have their specific formatting for referencing because, of course, that's it's very important that they understand where the information that you're presenting came from. I'm not going to be that strict. You can use whatever formatting you want. In fact, it can be a loose formatting, just so I know where the information came from. If it was a journal or what the article name or something like that was. And for other people, remember, your fellow students are going to be reading these. Maybe I'll find some way to make them available to everybody on a Dropbox or something like that. So when we're all done with this, if you guys want to go back and compare each other's work, maybe you can do that. I'll make that voluntary. If you don't want to be there on it, if you don't want to be on the Dropbox file, I won't put your stuff there. Okay. Okay. So, okay, good. I think we got all the questions out of the way on this. Now, assignment number 5, we got a few questions about that. I have to grade them individually because they're documents and so on. So I'm not done with all of them. When I'm done with all of them, I'll release the grading on them, and you'll all see the grades on them at the same time. It'll take me another day or two to get through them, and you will still have until the 25th or the 27th. You will still be able to resubmit it as it goes for all the homeworks. Resubmit it to raise your grade on homework. Um, 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 and as far as any more assignments are concerned, I may give you one problem on analysis of variance, one problem on correlation, and maybe just make it kind of an extra credit or a optional, maybe just even optional. So you could give it a try, and I'll just check your work and make sure you make and give you some feedback on it or something like that. But I don't want to burden you with something else when I know you're concerned about the project. Okay, so I think we got all that out of the way for now. So my plan for tonight is to introduce you guys to correlation and regression, linear regression. Okay, an important topic in statistics. Regression, linear regression, multiple regression uh, and other kinds of regression are very critical topics to advanced statistics. In fact, as I mentioned to you guys, that and logistic regression, you can take entire courses on them. You can devote your life to them, basically, as some statisticians do. And kind of like being an actuary, right? I'm not sure how many of you guys would want to do this full time all your lives. Anybody here inspired enough by this to be a statistician? I'm not seeing any. I don't know about online, but I'm not seeing any hands in here. But it's interesting, and when you see this stuff, see the kind of stuff that you can get involved in when you really learn a lot about advanced statistics. When you see what a powerful tool it is, maybe in a future course or something like that. Or when you're in EPI and you see what people have been able to do with statistical analyses, you might be a little bit more inspired by it. Okay, so at any rate, so let's talk about this idea of correlation and regression. I've talked to you about many times about certain terms in statistics that don't sound like what they are. For instance, analysis of variance is really a way to compare means, but they call it analysis of variance. And we discussed why that is. Variance between the means of three different groups and variance within the groups has an influence over whether or not you're able to, with some level of probability, distinguish between the means of those populations. Okay, so analysis of variance really means comparing means. Tonight, we have two terms we're going to get introduced to. One is called correlation. The other one is called regression. Correlation correlation statistic means very similar to what you would think it means in English. Okay, it means, is there an association? Is there a correlation? Does one thing influence something else? Okay, and I'm gonna break with tradition here and maybe kind of go through basically what's kind of a PowerPoint. Okay, it's not really a PowerPoint, it's a PDF file, but just so I can give you some insight into this. Let me see if I can't find it. I think this is it. Oh, I think I had it open. Okay, so here we go. Correlation and regression. Okay, so where would we use correlation and regression? Well, we've worked with situations where we're comparing the means of two populations. In other words, population A and population B. Population A, we drew a sample from population A, we drew a sample from population B, and now we want to determine whether the average for some variable is different between those two populations, which is a numerical variable, but we're factoring it using a nominal variable. Country A, country B, placebo, drug, intervention, no intervention. So that deals with that shows us how we can deal with. We use a t-test, we use confidence interval. We had tools to deal with comparing the averages, the means of two different groups. Okay, so then we looked at well, how about comparing the averages in three different groups? And we learned about analysis of variance very recently as a tool to compare the means of group A to group B, group C, group D, and so on. So we get multiple groups at the same time. Can you see that up there? Yeah, I guess so. All right. So we had a tool to deal with that. Well, now what about categorical or nominal data? In other words, whether a person has diabetes, well, excuse me, whether a person drinks a lot of sugary drinks and whether they have diabetes. So two categorical, if we look at them as categorical variables, not as the number of drinks, yes, they drink a lot of sugary drinks. No, they don't drink any sugary drinks. Versus do they have diabetes? Do they don't have diabetes? Those are two categorical variables. We can't do averages. I mean, there's not an average for it. Let's say if we said diabetes was 1 and no diabetes is 2, and we did an average and it came out to be 1.1, it really wouldn't be meaningful, right? We really need to look at that as nominal data, as a probability, right? What's the probability someone that drinks sugary drinks has diabetes? What's the probability that someone doesn't drink sugary drinks have diabetes? And look at those proportions and compare them, right? So we needed a method to deal with that, and we found a couple of basic tools there. We found that we could use something called odds ratio and relative risk to determine whether it's more likely that a person that drinks sugary drinks has diabetes, or whether it's more likely a person that doesn't drink sugary drinks has diabetes. So we use this statistic called odds ratio, odds or odds ratio, risk or risk ratio, to compare the rate at which those two populations might have diabetes. We also learned a statistic called chi-square, where we could arrange the data into tables and determine whether that table is really representative of what we would expect if there was no association between people that drank sugary drinks and diabetes, right? And now when you're working on your projects, right, you're going to be looking at what kind of data that you're evaluating. And if it's categorical data, like got a flu shot, didn't get a flu shot, has insurance or doesn't have insurance, you might be looking at that kind of analysis because both of those are nominal variables. Okay. Now, what about when we have something that's that both sets of data, both variables are both numerical? For instance, this data that we're looking at right now is the annual consumptions of average consumption of cigarettes in the United States, in Great Britain, in Iceland, and in a number of different countries. Okay, so that's a numerical variable. What's the average number of cigarettes smoked per year for a person living in the United States? Okay, now this is 1930, so this is Humphrey Bogart and and all sorts of other movies where everybody's smoking cigarettes. Which is the movie where what's his name? I forget the actor's name, where he lights up two cigarettes at the same, very romantic, lights up two cigarettes at the same time and hands one, I think, to Betty Davis or something. Now Voyager, was it Now Voyager or something like that? But at any rate, she dies at the end, so you don't have to watch the movie now. So at any rate, they smoked a lot of cigarettes in those days, so maybe 1,300 is realistic. And lung cancer might be the number of cases per 10,000 people. 20 cases per 10,000, 46 cases per 10,000, and so on and so forth. You notice it's higher in Britain than the United States, but in general, look, we can kind of see that countries where they smoke fewer cigarettes, they seem to have lower rates of lung cancer than countries where they smoke a lot of cigarettes. But they're both numerical variables. It isn't yes I smoke, yes I smoke, or no I don't smoke, versus yes I got lung cancer, no they didn't get lung cancer. That would be nominal variables. You use chi-square, odds ratio, relative risk, right? So this is numerical data. Now anybody, and look, it's almost, you can see it's kind of interesting that it goes down like this. Anybody think of a reason why they would smoke less in Great Britain but still have higher rates of lung cancer? See how much history you know. There were periods in Great Britain, particularly around the big cities. What did they use for cooking and for heating? Coal, right? Exactly. And they would have a lot of coal burning stoves, ovens, so on and so forth, indoors in houses. And there were times when and the weather there is always constantly raining. They get these thermal inversions. And there were periods when the outdoor air, was virtually unbreathable. They would have people collapsing on the street because the air was so bad. People with respiratory conditions, right? So they had very bad air as associated with the amount of coal burning that they were doing, even indoors, So maybe that has something to do with it. But in general, I'm getting a feel for this, that it seems like there's an association between the rate that people are smoking and the the rate at which they're getting lung cancer. So we need a way to express this. Okay, so we know that for each one of these things, cigarette smoking, lung cancer. Well, I'm gonna guess that cigarette smoking is the exposure, and lung cancer is the possible outcome. Okay, we're going to talk about correlation. For correlation, it doesn't really matter which is which, but you'll see that why in a second. So I'm curious to see if I can really show that there's an association between these two numerical variables. And one of the ways I can is to plot this on a graph. And the way I'm going to plot it on a graph is I'm going to take the value for the number of cigarettes smoked, 230, and plot it with the number 6. So in other words, 230 and 6 represents a point on the graph. And if I do that for each point on the graph, this is what it looks like. Like this is 240 and 6, right? In other words, I define the cigarettes as the x-axis and the number of lung cancer cases is the y-axis, and I plotted all these. Okay, and what do you notice about this? It's linear. It looks kind of linear, that more cigarettes you smoke, the more cases of lung cancer you get. Now, I got a couple of excursions there. One is this country over here, which is, let me go back and see which one that might have been.
Finland.
That was Finland? Okay.
That's Great.
That's Great Britain, right? Almost 40, right? Exactly, which we decided we kind of understand why that might be an outlier, right? And the other one was, which seemed lower, was, which one was it? Let's see, 1,300 cigarettes. That's the U.S. Seemed a little bit lower, and I'm not sure why that might be. Maybe we started smoking them a little bit later than in Europe. Who knows? Because there's a long latency between cigarette smoking and lung cancer, right? So who knows why that might be? But we see that there appears to be a relationship between the two of these things, right? So we want to demonstrate whether that relationship is by chance or if there really is an association with cigarettes and lung cancer, right? So the first thing we do to examine this is we produce a scatter plot. This is called, when you make these dots up, which represent x and y axis, representing the different variable values, right, bivariate values. You can get a look at whether or not there appears to be an association, right? So one of the things you might do there is you might want to know, well, number one, does it look like a straight line or does it curve? In other words, does it kind of go up here and then curve? Are there outliers and so on and so forth? But this looks pretty straight, right? If I drew a line that's the best fit between all of these points, it looks like it would almost be a straight line, right? So now we're going to talk about how we're going to define a best fit in a moment. Okay, so direction, does it tend to point upward or downward? Well, this one points upward, which would suggest that as you increase the exposure to cigarettes, you increase the risk of lung cancer, right? Or the rates of lung cancer. Now, we might have situations where things point downwards. For instance, as you increase the amount of fruit and vegetables you eat, the rate at which you get colon cancers, right, the rate of colon cancers might go downwards, right? So some of these exposures are protective. Some of these cause disease, right? And another one of the things we're interested in, besides that line, whether it's linear or not, is whether or not it slopes upwards or downwards. That would indicate the nature of the exposure. Strength of association, how close do they adhere to a straight line? Well, down here, it looks like it's pretty close, right? Up here, things get a little, when we get up to really high consumption of cigarette, it gets a little bit iffy up there, doesn't it? Okay. And outliers, okay, and we see that there are a couple of outliers. We kind of can explain this one away. We're not so sure about Finland over here, but there might be something. So we're concerned about outliers. Okay, so now how do we judge the strength of that correlation? How good a correlation is that? Well, if we look at the chart on top here, that's not a very good correlation, is it? Right? It's like it's not really falling on a straight line. We can see there's a general trend that as you increase the X value, the Y value increases also, but it's not a very strong correlation because there's a lot of variability. So this guy's all the way down here, way below this value, and this one's over here, and this one's below, these two values, and so on and so forth. But it's way up here. So there's a correlation here, but it's not very strong. Well, how about this one? Well, this one, you want to know something? There's a little trick here, right? This and this is the same plot. It's just the axes are different, right? So you got to be a little bit careful. You just want to you want to do a scatter plot to get an idea of whether or not you have a correlation, but you can actually kind of fool yourself by this is the numbers are condensed, more condensed here. The axes are more condensed on this one than that one is, but if you look at it carefully, it's the same thing, right? So, but yeah, so we want a numerical way to describe how strong that correlation is. And the way that we're going to do that is we're going to actually calculate it. We're going to draw a best fit line between all these points. And that best fit line, we're going to calculate the difference, the difference between where that line is and each value is, right? So the bigger the total is, now some of them are below, some of them are above, right? So some of them are going to be negative y, positive y for different x's. Again, we combine them since it's a best fit line. They're going to cancel out. So we're really going to be looking at the squares of the differences from the distance to an individual line, rather than the distances themselves. Okay, and we're going to calculate a number, which is going to be a smaller number if the correlation is very tight. If it's a good correlation, it's going to be a bigger number if the correlation is not so good. And actually, we're going to do a little manipulating with that number. So the way we're going to present that number is going to be a little odd at first, but it's going to be something that you're going to be able to work with. Now, one of the things I mentioned is, look, it looks like there's an association between smoking and lung cancer. When we're talking about correlation, we don't care about causation. We don't care that cigarettes cause, whether cigarettes cause cancer or the lung cancer makes you smoke cigarettes. We don't care which causes which, because we're just looking at the numbers and the association. When we get into regression, then we're going to be worried about what causes what, which one of these causes the other, which is the dependent variable, the y, and which is the independent variable, the x. In other words, the independent variable is a fixed value, and from that you determine what the y is, y-axis. Okay, so we're going to want to know that. So, for instance, is there a correlation between the number of firefighters that go to a fire and the amount of damage that occurs at that fire? Yeah, I'd say so, right? You get 5 companies and 100 firemen showing up to a fire, probably a lot of damage, right? You get 1 fire truck showing up, with a fire extinguisher and 3 firemen. You're probably not a lot of fire damage, right? Does that mean a lot of firemen means they're causing a lot of damage? No. There may be an association between the number of firemen and the amount of damage, and that correlation may be a real correlation, but it doesn't mean that the firemen cause it. It doesn't require causality at all. We don't care about that when we're describing correlation. Again, when we're talking about a regression, things are a little bit different. And also we want to avoid, there's occasions when you'll come across coincidences when there's a correlation, right? But there's no now this is kind of an obvious one where you could see that there's no. Do an exercise. Okay, and you guys, if you want, you can open SPSS. I think you can either copy these numbers in, or you can copy and paste these numbers in, or you can type them in, or I think I also have them on Blackboard as a data file. Let me see. Let's see. Let me see. Let's see. Where am I looking here? Not sure which one that is. Let's see. Where am I? Let me get another look at this. Time-based randomness, like the long-term facility, age and blood pressure. Do I have that file there? Yeah, if you want, you can download that to your desktop and open it, or you can just cut and paste it. Do I have that there? Is that, which one is that? Oh, yeah, blood sugar. Okay. So I got to do that myself. I'm going to right-click on it, and I'll save the link, put it on my desktop. Okay. So I'll work on that with you. Okay, I'll open SPSS now, and I'll open that file. Okay, let's just looking at that data. Do you see the association? 30, blood sugar 75, 110, 44, 52, 60, 140. Looks like as you get older, your blood sugar goes up. This is all, it's all fake data, of course. But we're going to take a look at this in terms of, is there an association? So I'm going to say open data. Since it's an SAV file that I've downloaded, it should be on my desktop. I'll navigate there. And it's looking for SAV files, so it finds it. There we go. Okay, it imports it. And there we go. Okay, so we have age and we have blood sugar. Both of these are what kind of variable? They're numerical variables, right? And then if we look on our variable view, you can see that SPSS identified them automatically as being what it calls numerical variables. It refers to them as scalar or scales. And you'll notice it uses a symbol like a little ruler. So if you're working in some other area and you're importing data or you're working with data, you can use that little scale to represent, that little ruler to represent a scale or a numerical variable, sequential chart, sequential bars to represent ordinal, and different colored balls to represent nominal. Okay, so now I'm going to go back to SPSS again. Going to go back to the data view. And we want to find, first of all, is there an association here? So what's the easiest, quickest way for me to get a feel for whether there is or not, without using math? How about if we create a scatter plot, just like we did before? So I'm going to go to graphs. I go to legacy dialog, just to keep things simple, because it's the simplest way to get to it. Scatter dot, scatter plot or scatter dot is what we call this kind of graph. I'm going to click simple scatter dot. I'm going to click define, and it asks me to fill in the X and Y axis. Does it matter which one I put in the X and Y axis? At this stage, no. When we talk about regression, I'm going to want to know, well, gee, which one causes which? High blood sugar doesn't cause old age, right? Doesn't make you any older, right? But your age may influence your blood sugar. So the causality is in that direction, right? So I would want to put, in that case, I would want to put age into the x-axis and blood sugar into the y-axis. I could do it either way here. Just to be contrary, I'm going to do it the opposite way here and see what we get. I'm going to click OK. I'm not going to bother with titles or anything else. I just want to get a quick graph. And let's see, as blood sugar goes up, age goes up. Does it look like I have a linear relationship here? Right? Does it look like there's a relationship between blood sugar? Sure it does, right? And it looks like that relationship is linear, right? It looks like it's not going up and tailing off, or it's not asymptotic and going up, or it's not like asymptotically going down or something like that. It seems to go in that direction. In fact, SPSS will, even in this point, it will draw a line for us. I'm going to add a fit line, okay, right here, and it will draw that line for us. Okay, and there's that line, and that line is drawn in a way that all of the differences squared between all of these values evens out. Okay, so So I'm looking at that line, and that line would represent a perfect fit. If all of these dots landed on that line, that would be a perfect correlation, right? And yes,
Which is that best fit?
it's under. If you hover over these, it'll give you a hit, add fit line, add markers, and so on and so forth. Let me tell you, I, I kind of, I didn't realize that I was just like doing that so quickly that I didn't really give you kind of a background on this. I'm going to go to graphs, legacy dialogues, scatter dot. Okay, I'm going to click simple scatter dot, define. Now this time I'm going to rearrange them, put them this direction. I'm going to say age is my x-axis or my independent variable. X-axis is independent. Y-axis is my dependent variable. When we get to the next step, regression, it's going to make a difference, right? So that's the way I'm going to do it this time. Okay, in fact, that's probably a good idea to do it all the time, but I was just demonstrating it doesn't really matter. Okay, so I created a new graph. And you can see it's a little bit different shape, but we got the same idea. As age increases, most people's blood sugars are higher. Again, bogus data, but but just for a demonstration purpose. Now let's say I want to edit this chart or this graph. If I had a chart here I wanted to edit, well, actually it works same way with both charts and graphs. If you double click on the graph, it opens up an editor window. Okay, same thing with the chart. And now I can do all sorts of things. I can highlight text here and tell it that I want to change the color of the text, for instance, and so on and so forth. Right, I'm going to close that. Now, one of the things I can do that involves a calculation is there's one of these options that will add a fit line. Okay, don't worry about that part at total. Okay, and it actually creates that line which represents a best fit for all of these different points, for a straight line that would represent all of these different points. Again, that line, if it were a perfect correlation, all of these dots would land on that straight line. Okay. Now this one, they don't all land on that straight line, but most of them are pretty close to that straight line. The closer that they are to that line, the more predictable they are, the tighter, the more tightly associated one variable is with the other, and the correlation is greater. We're going to put a number on that correlation soon, right? So if these were scattered more, it would be less reliable correlation. Okay, so we want them to be close. Okay, so I'm gonna put this away for now. Okay, and it leaves that in there, so you'll have that if you want. It also gave us a formula and a number called R squared up here. We're going to get to what that stuff means very shortly. So now we numerically want to calculate whether or not this is a good fit or not. While I'm here, can you tell me something? What about the slope of the line? It's upwards. What does that tell you? That as age increases, what happens to blood sugar? Increases also. If it had been downwards, it would have been the opposite. As age increases, I don't know, visual acuity decreases, let's say. Okay, so it depends on the variables, the nature of the variables and their relationship. In this case, and what is the core? We're gonna when we get into regression, how much it increases or decreases is going to be important to us. Okay, so we'll see that in a moment. So now let's actually see if we can do some calculations here. I'm going to say analyze. I'm going to go to, we have a solution here. We have a analysis called correlation. And I'm going to go over to bivariate. And I'm going to tell it the variables. Now it needs two variables, bivariate. Okay, I'm going to put the age in there and blood sugar in there. Notice for correlation, it doesn't ask me which one's the independent variable, which one's the dependent variable. It just asks me which are the two variables that you want to check. Okay, we're going to use something called Pearson's correlation. Okay, it's a method that he invented. So I'm going to click OK. Okay, and I get a table that comes up, and it tells me that the association between age and age is 1. In other words, if I looked at a person's age and compared it to his age, I'd get the same number, which is obvious, right? So it's kind of like, this is kind of like really not very useful, right? Because I'm only comparing age and age, and I get the Pearson correlation 1. What does that tell you about the number 1? A number one represents a perfect correlation when you talk about Pearson's correlation. And Pearson's correlation is represented by lowercase rho, r, lowercase r. Okay, so what about when we compare age and blood sugar? Well, the correlation is 0.821. Well, gee, 0.821. That is closer to 1 than it is to 0. So what does that suggest to you? It's a good correlation. If we're closer to 0, it's not a very strong correlation. In other words, those points are scattered more than if it was close to 1. So this is a pretty good correlation that we have here, 0.81. But is that correlation due to chance, or is it due to a real association between these two variables? And that's where we come down here to the p-value or significance. Okay, and it's equal to 0.004. What does that suggest to you? Does it suggest to you that the correlation is due to chance or that there's a real correlation? It suggests there's a real correlation. How would we express that as a hypothesis test? Right? Well, let's think about that. What we might say is that a correlation of 0 means that there's no association, right? And a correlation that's not 0 means that there's at least some association, right? Maybe it's, whether due to chance or not due to chance. Well, if the hypothesis is that that there's no association, it's our null hypothesis, when we get a value less than 0.05 here, we can reject that idea and say that there is an association. So that's kind of a way you can look at it as kind of a hypothesis test. So in order for us to say that this is a statistically significant, that there's a statistically significant association, we're going to look for this to be less than 0.05. Okay, so and very frequently, like that'll be the case. If you have a lot of data, as you do in some of the numerical variables that you're going to be working with, there's a lot of likely you might actually find some significant associations. Now, you could get a correlation which is 0.1, which is not a very good association, but still see statistically significant. Right? What does that tell you? Well, it tells you there's an association. It's not a strong association, but it's not due to chance either. Okay? So there's a few ways we could interpret this chart. Now notice it does exactly the same thing in the opposite, compares blood sugar to age, gets the same result. Right? So now what do you think the chart would look like if this came out to be a negative 0.821? Anyone want to take a wild guess? Sloping downwards instead of sloping upwards. If the chart is sloping downwards instead of sloping upwards, the correlation would be a negative sign instead of a positive sign, right? So -1, +1, both are perfect correlations. One sloping upwards, the other sloping downwards. Okay, so that's our correlation. That's our association between these two variables. Okay, let me go back to this and see if I suggest you what type of variables are they. They're both numerical variables. We plotted them, and so on and so forth. You could do it in Excel or SPSS, as you can see here in SPSS. Okay, so now, and it's pretty. We have a strong association. It's positive as age goes up, blood sugar goes up, and it's statistically significant. In other words, it's not due to chance. Okay, so now let's look at this idea of regression. Now, the word regression really doesn't have too much to do exactly with what we're doing right here. The reason why it's called regression is because the person who developed this, the statistician who developed this, was demonstrating, was using statistics to demonstrate something that he called regression to the mean. Okay, and that is, for instance, how can I describe that? Let's say that you get two very tall parents, right? And they have a child. Would you expect that child to be, remember that they're taller than the average person. Both these people are taller than the average person. Would you expect that child to be more likely to be taller than their parents or shorter than their parents? What do you think? Could go both ways, but which is more likely, do you think? Wrong. Wrong. Yeah, wrong. Now she's taking, yeah, oh, I knew it was her. Go ahead,
No,
okay.
we didn't know, but I
Yeah.
did have one. I
You know
saw
why?
Carlos having
Think
one.
about it for a second. If you get two people that are 7 feet tall, that's like 1 in 1,000. Not even, probably 1 in 10,000 people is 7 feet tall. So you have two people that are 7 feet tall, and they get married and have a kid, right? What are the odds of having a kid that's 7 feet tall too? The odds are good they're gonna have a tall kid. But 7 foot tall, that don't happen very often, even with two parents that are 7 foot tall. So the idea here is that the extremes, very short, very tall, a lot of beans, a plant with a lot of beans, a plant with not many beans, right? That when you mix them, right, that the offspring will be closer to the mean. When you combine two extremes, the offspring will be closer to the mean. That's called regression to the mean, right? And he was experimenting with statistical techniques to demonstrate that. This is kind of where this all kind of started. That's why the process is called regression. We're not going to use it that way, but that's where the term comes from. But it's interesting, right? When you think about it, that makes sense, right? If you mated two of the fastest horses in the world and they had an offspring, you would expect a fast horse. But you'd have to be really lucky to get a horse that was as fast as their parents, right? What did you think? I see a lot of skepticism here. Okay, trust me on that. Okay, if that were true, if it weren't true, then you might as well not breed any. You should only breed the horses that are the fastest, and that means every time you breed the horses, that horses will get faster and faster and faster until they were like the Flash on TV. You know? So if you didn't have regression to the mean, imagine what that would mean in populations. That would mean you get ever increasing extremes if you didn't have regression to the mean. Okay, so at any rate, so let's take a look at this. So regression, we're going to take this data file that we just were working with. I'm going to go back here. I think there's material in your book that covers this. I know there's some if there isn't a lot of stuff on regression, I should give you like some other reading or something like that if you want to follow it. So I need to check on that. So I'm going to go to analyze. I'm going to go to, now we saw correlate, right? Now we're going to go to regression. Well, now this means something here. Now, one of the reasons I'm not going to talk too much about logistic regression is because it's an advanced topic, number one, and number two, you don't have if you have the base version of the graduate student $45 version of SPSS, you're not going to have logistic regression as a selection here, but you will have linear regression. Okay, so this is linear regression because we're expecting this data to basically be linear. Okay, so now, what does it ask me? It asks me for the value for the dependent variable, right? The dependent variable is the one that depends on the independent variable. So the independent variable is going to be age, and the dependent variable is going to be blood sugar. Age determines what the blood sugar is going to be, okay, not the other way around, right? So we can agree on that. It's important in regression because regression, we're concerned about causality. Correlation, we're not concerned about causality. So I'm going to click OK and have it do this calculation and see what it gives us. Oh, you know, I can't believe I jumped ahead to like this. Okay, well, that's okay. Let me go ahead. I'm okay. Linear. Okay, I'm going to go back and put age in here, put blood sugar up here. I'm going to click OK. You guys remember what Pearson's R value was, rho value was? It was 0.821, right? It recalculated the correlation, right? And here it is 0.821. Okay, so now it also calculated a statistic that it called R squared or rho squared, which is just 0.821 times 0.821, and it just stuck that there. That's a value called R squared. We're going to come back to that value in a moment. Okay, so it does another, and believe it or not, the statistical analysis that we're doing is basically an analysis of variance, and there is where our value that tells us whether this result is significant, this association is significant. That's our 0.04 that we got before. Okay, and in fact, we're going to see some other statistical tests as well. I'm not, for now, we're not going to worry about the ones down here. We're just going to really focus our attention here on this thing called unstandardized coefficients or coefficients. Okay, so now, what is the information that we're getting here? Well, this R and R squared is a measure of how associated these two variables are, right? And we can see that the association is strong. And this R squared number is pretty big too, right? Bigger the R is, obviously bigger R squared is. Okay, down here we get a couple of numbers. One is called a constant, and one of them is a variable that's a coefficient that's associated with age. Well, now I'm going to go back here, and I'm going to get my blackboard here. And I'm going to take a look at the idea of a little bit of what we've learned many years in the past about age, about lines. Okay, so here was our blood sugar, and here is our age, right? And as age went up, blood sugar went up. So we had values over here. It appeared linear, right? And when we draw a fit line, it went something like this. Now, how can I describe that line? That line gives us the ideal association between age and blood sugar, right? If I could draw that line and I knew someone's age, I might be able to use that to predict what their blood sugar is going to be at that age, or what I would expect their blood sugar to be at that age. That would be pretty useful, right, in some situations. Okay, so I need some way of describing that line. Well, when you took algebra, you use the formula y is equal to mx plus b, right? Okay, anybody remember what those numbers were? What did m represent? Slope, right? That represents slope. What did b represent? The y-intercept, right? Where it crosses the value, where it crosses the y-axis when x is equal to 0, y-intercept, right? I missed that. Did I miss something? Okay, good. So at any rate, we use that in statistics also, except a lot of times what we'll do is we'll say f of x, right? Our dependent variable is equal to a, I may get this wrong, a plus bx, right? Where a is the y-intercept and b is the slope, okay? And what is the slope? Slope is the distance you travel up over the distance you travel horizontally to get from one point to another point, right? So that represents the slope. Remember that value over here for age, right? That the coefficient is an age. The slope for our line for age versus our best fit line is equal to 1.762. So f of x is equal to a plus 1.762 times x. Okay, what is a again? That's the y-intercept, right? So let's see what that was here. That's 17.46. That means that at the point where age is equal to 0, now remember that the y-intercept may be meaningless, right? So at age equals 0, before you're born, you're not going to be taking anybody's blood sugar. But at age 0, if we carry that line over, it crosses at 17.4. 17.5, let's call it. Right? So f of x is equal to 17.5 plus 1.762 times x. Well, now what is f of x and what's x? Well, this is blood sugar is equal to 17.5 plus I'm going to call it 1.8 times x, right? That formula represents our best fit line. And we can use that predictively, okay? So if you tell me what someone's age is, I can calculate what I think their blood sugar will be. The better the correlation is, the better my predicting values are going to be, right? And that's really what gives regression kind of a lot of power. Is a couple of the ideas here. Number one is that the slope, 1.8, gives us an idea of how age influences blood sugar. For every 1 year that you go up in age, you go up 1.8 in blood sugar. For every 10 years in age you go up, your blood sugar goes up 18, whatever that value is, micrograms per deciliter or what, milligrams per deciliter, whatever it is, right? Um, um, so it gives us an idea of the magnitude of impact of age. Now remember that number we got, that R squared? The reason why that's of interest to us is because it tells us what percentage of the variability in the independent variable is due to the independent variable. In other words, 64% of the variability in blood sugar is due to age based on our calculations. What does that tell you? That tells you that 36% of the variability is due to other factors. But man, if we had, if we could come across results like this all the time, it would be great. Remember, we faked this, right? That we could, 64% of the variability blood sugar is due to age. Well, then I could concentrate on, treating people as they get older more aggressively for elevated blood sugar and so on and so forth. Could be that really in real life it may only be 10 or 20%. And other factors, obesity, BMI, so on and so forth, maybe the many other factors, diet, so on and so forth, maybe among the other factors. But you see the kind of power that we have with this? It helps us not only understand how, if there is a correlation and if it's statistically significant, but how one variable affects the other, and how much of that variability can be accounted for by that other variable. Okay, so let me see if we got a couple other examples here. Okay, and I'm gonna move this over. I want to get to these. I want to go down here to comments. Do you guys have any questions online about that? Do we have any questions online? You guys okay with that so far? I just want to let me back up on a couple of questions here that came up. Okay, so far so good. Okay, good. As far as like when the project, I'll get into this more on Wednesday. Just bring in the white papers. Print out your project on 8.5 by 11 paper or whatever you want to print it out on. I will bring poster boards down with thumbtacks, right? So that you can, or push pins, so that you can mount them on the push pins. No, I'll bring the poster board and the push pins. You just bring your printed presentations in a form where you can just pin them up, and go through it and so on and so forth. Did you see some of the pictures? Did I show you guys some of the pictures of the other ones? Where if you look at the document that describes the project, that Word document, the last page I've added some photos of students from last semester standing in front of their presentation, and you'll see they have 8.5 by 11 pieces of paper and they're tacked up. But I'll bring the hardware. It would be hard to fit more than 9 sheets of paper. I'm sorry, most of the examples were 9. What? Oh, is that what on the ones I put up? That's just coincidence. Yeah, that's just coincidence. I mean, if you look at the poster board, whatever you can fit on there. I mean, there's no limit. There's no limit on either way, except that, if you bring in 40 pieces of paper and we got to use 8 pieces of poster board, something's going wrong. So, right? So, you want to be reasonable, right? And probably if you get everything into 2 sheets, and either you're printing too small or you haven't done enough. But I wouldn't worry about that. But yeah, I wouldn't worry about the specific number of pages. Okay. So, okay. I would worry mostly, what I really is the best? Clarity. If you express yourself concisely, if it's easy to understand the information you're presenting, that really works. That's really what works the best. Remember what we're emulating is something that takes place at conferences all the time. And there are rows, there might be 100 people with posters up, maybe 200, row after row. And people that are attending the conference They might be going in to a large auditorium to hear a paper being presented, but many other people will be presenting research that they're working on these poster boards, and they'll be lined up in rows, and you just walk down the row and you're glancing on them as you go by. And then, like for instance, I'm interested in Legionnaire's disease. If I see a poster board Legionnaire's disease and evaporative coolers or something like that, I'm going to stop and I'm going to read that one, right? And if the person happens to be there standing next to it, I'm going to be talking to them about their research, what they found and so on. But think of it that way. You want to grab somebody's attention, and you want them to be able to think. Imagine that you're going to go to the bathroom, have lunch, and so you're not going to be standing next to this thing 24/7. Did you guys read something about they had this big deal going on the Upper West Side because the police came in the middle of the night one night and confiscated all the books from the booksellers that put out their tables and stuff like that on Broadway? You guys ever notice that on Broadway? There's an area of Broadway on the Upper West Side where there's like table after table of guys selling books, used books and stuff. Yeah, I think some councilwoman made a big deal about it and had the police go and confiscate. That there's a technicality. You do not need a permit to sell books on the street in New York City, as long as you're not obstructing traffic or flow. You don't need a permit. You may have to have a business license. You got to charge tax, right? But you don't need a permit because it's literature. It's like freedom. It's a free speech issue, right? You don't need a permit. Now, in New York City, they have an ordinance on that, and booksellers, they can, as long as they're not blocking the street, they can have it up there anytime they want, day or night, but they have to be attending the tables, right? A lot of these booksellers, they leave them up there and then they cover them up, when they leave, or they go to the bathroom and have dinner or go home or sleep or something like that. And traditionally, they just left the stuff there and they would come back the next day and sell their stuff. Not like that, kind of like the guy out here with the incense and the other stuff on the corner. He comes and goes. He takes his stuff with him. The booksellers a lot of times leave him. So this councilwoman made a big deal about it and got the cops to go over there and confiscate all the books. And now there's like a whole big deal going on there because a lot of the people like that. That's kind of the flavor of the Upper East Side. So they're kind of angry at her for like setting the cops on them, and now like people are donating books to them or something like that. A big drive to donate books. How did I get on this tangent? What was I talking about that made me think of that? Right? What made me think about the fact that they were? Anybody remember what I was talking about anymore? Huh? Oh, the poster boards. Yeah, the poster boards. Right? It's like just like those guys. You may want to go take a nap somewhere or have lunch or something. That's what reminded me. You may want to take that. So you want a poster that is self-explanatory, right? Because you want to be able, somebody that's coming by can read and understand your research and so on and so forth, and maybe then contact you afterwards. Sorry again, I can't help myself sometimes. So at any rate, so that's what we're dealing with there. Okay, so that's what regression is. That's what our correlation and regression. That's how we express it numerically. Let's do another example. Okay, so I'm going to go back, and I am going to. There's a few data files there. I'm just going to pick one randomly. Let's see. Let me go back here. And let's see, I think we got, how about violent crime? I'm not sure what's in there. Actually, I'm going to download two of them. Save link as desktop. And just in case it doesn't. Okay. And let me open up that data file. Okay, so let's see. Open data. Okay, and I'm going to go violent crime. Okay, yes, whatever that is, whatever the objection was there. Okay, here's where we have something interesting here. Okay, here's different states, and here is some data from those different states. One of the variables, numerical variables, is the murder rate. And one of the other ones is the poverty rate. Okay, maybe that's the percentage of families in that state that are below the poverty level. I'm not sure how they got that number, but they're both numbers. They're numerical variables, right? So if they'd both been categorical variables, we would have said chi-square, odds ratio, relative risk. If the one was a categorical variable like poverty, yes or no, and murder rate, we might have used we might have used t-test for analyzing, comparing means. If there was three groups for poverty, three income groups, we used the analysis of variance to compare the means of three groups, right? But this is actually two numerical variables. Okay, we have the murder rate and the poverty rate for each one of these states. Okay, so what's the first thing I might want to look at to see if there's an association here before I go crazy doing a lot of calculations? Scatterplot. Yeah, let's look at it graphically. Okay, so I'm going to go up to Graphs, Legacy Dialogues, Scatter dot. And I'm going to say simple scatter dot. Again, it's not. It doesn't matter what I call the x-axis, what I call the y-axis. So I'm going to put in murder rate. And I'm going to put in poverty. And I'm going to click OK. Okay, let's see what this scatter plot looks like. Well, it's kind of hard to tell, isn't it? Because it's so condensed. And why is it so condensed? Why did this happen? What is this over here? What? Yeah, what happened? There's a big outlier. Like, who the hell is that? Who has a murder rate of 45 per whatever it is, 10,000 or something like that? Let's take a look at that. Okay, let's see where that is. Murder rate. Okay. Oh, there it is. Is that it? District of Columbia. It's not even a state, right? It's more of a city than a state, right? And it could be maybe there was an incident there where there are a lot of murders in a short period of time or something like that. It's a small population, so that could affect maybe they had 10 extra murders, but it's a small population, not like a state. So you know what I'm going to do? I'm going to remove that outlier, and I'm going to redo this analysis. Okay, let's go do that again. And in other words, I've given a reasonable explanation for why that might be an outlier and why it might be appropriate to remove that from the analysis. Analyze. Graphs, legacy dialogues, scatter dot. Okay, simple scatter dot. Okay, and the variables are still in there. Let's run this again, and let's see what it looks like this time. Now we get a little bit better picture of what's going on in here. Does it look like as the poverty rate goes up that there's an association between the poverty rate and murder rate? It looks not very strong though, right? But it looks like there is some association. And I could double click on this and ask it to actually plot that line for me. And look, this time you'll notice that when it plotted that line, it also calculated for me what the R square was and what the formula for the regression is. It actually gave it to me, just with that one click. We're going to go through the exercise of actually doing it anyway. Okay, I'm going to close this. So let's see if there's a correlation. Let's go to Analyze, Correlate, Bivariate. And I'm going to move the murder rate and the poverty rate in here and click OK. And indeed, it calculates that the murder rate, there's a correlation between the murder rate and the poverty rate is 0.427, and it's statistically different than zero, than no correlation. So there is an association between the two of them. It's statistically significant. There's less than 5% chance that it's just due to chance. Less than 5% probably is just due to chance. But the correlation is only 0.427. It's not as strong an association as we had when we did the last problem that we had, right? So now let's do our regression. Analyze, regression, linear, and which one is going to be the independent variable? Poverty or murder rate? Poverty, right? Because that's the one that's going to predict the dependent variable. And murder rates are a dependent variable. I'm going to go ahead and do the calculation. And let's see what we get. Our R value is 0.427, and when you square that, you get 0.182. Only about 18% of the variability in the murder rate can be attributed to the poverty rate. That means most of the variability in the murder rate is due to some other factors. It's not like it doesn't have an influence, right? It's 18%. but most of the variability has other there's other reasons for it as well. Could be that some states are open carry states and they decide to have conventions in them. Who knows what the reason could be? Could be a lot of reasons for it, right? But we're not analyzing that. We're only analyzing these two variables. And what about our formula, right? Well, our formula, our slope is 0.365. Well, what does that tell you? That tells you that for every increase in the poverty rate of 1%, you only get an increase of about a third of 0.36 in the murder rate, right? So that gives us an idea how one influences the other. And our y-intercept is 0.432. Now let me see how that looked compared to, let me see. Here you go, same thing as we got here. See the line, the fit line that it gave us was 0.432 actually, and 0.036x. So if there is some amount of predictability here, but it's not as much as we might really want. So we're gonna when we get on this next week. When we get on this on Wednesday, when we come back to this, I may introduce a little bit of the idea of multiple regression or logistic regression. We're going to spend only maybe about half hour, okay, and then we'll worry about dealing with the project and stuff like that, and issues that come up with the project. Maybe a half hour to an hour, let's say. Okay, so, and maybe answer questions on the homeworks if you guys are still having issues with some of the older homeworks or something like that. Okay, let's try with one more data set. Open data, and I'm going to open up this violent crime. Did I download another one? I don't know where it went. Okay, let me give it a try. I thought I did. Thought I did more than one. Oh, maybe I didn't do a. Yeah, maybe I downloaded the wrong file format. RCF was an Excel file. That's it. Well, maybe here. This is good. This is an instruction. That's good. This is an instructional mistake that I made. Okay, so now let's say I don't see on my desktop. I don't see that Excel file. The reason why I don't see that Excel file is because right now SPSS is only looking for the .sav files, SPSS files. So I can tell it to either look for Excel files also, since I know that's what I'm looking for, or just simply all files. I'm not going to say all files because I have too much junk on my desktop. So I'm going to stick with Excel files. Okay, and sure enough, now I can see, in addition to the SPSS files, I can also see the other files. One of them is arsenic and well water. I'm going to click on that and say open. And it shows me that there is data between A1 and H329. There's a lot of data in this file, apparently. I don't remember it. I could have opened it up as an Excel file to examine it, but I don't remember. It's also asking me, is the name of the variable in the first row? I don't remember, but I think it might be, so I'm going to leave that checked off. We'll soon find out. When I click OK, it's going to import that data, and here's our data file. And indeed, the name of the variable was in the first row because now SPSS has used that name to name the various variables. Okay, so let's see what we have here. These are various towns, I guess, cities in India, I would think. Now, the UN, I don't know if I can track it down now, but the UN or World Health Organization, I don't know who was responsible for it. There were a lot of issues with waterborne diseases in different parts of India, and they put together a program where they supplied wells so that people in India that were using rivers and polluted rivers and streams and so on and so forth could pump water out of the ground and use it for drinking water, much less likely to be contaminated with various human pathogens, right? Because at least it's groundwater, it's not surface water, where you were getting, like the streams and rivers might be used for waste as well. So that worked out very well in terms of reducing disease from pathogens, typhoid, cholera, and so on and so forth. But one of the problems that they had was some of the areas where they did this, there were high concentrations of arsenic in the minerals in the ground. So people were now being exposed to chronic poisoning with arsenic, and they wound up with various cancers and there's skin conditions that are associated with exposure to arsenic and so on and so forth. So they found they removed one problem, but yeah, exactly, created another one. Although in the long run, a lot of people die from cholera and typhoid. So I'm not sure. I know not all communities had that problem, but in this particular situation here we have analysis that shows the arsenic level, and I'm guessing that that's parts per billion or something like that in these various different wells. And here's another variable that shows the depth of the well, how deep the well was. Well, maybe we can find a correlation between the depth of the well and the amount of arsenic that was present in the water. Okay, again, what's the best way to get a first look at this? Let's go do a graph. Analyze, legacy dialogues, scatter dot. Define, so you guys can do this while I'm doing it also. And let's take a look if there's an association between the depth of the well and the amount of arsenic. Whoops, got the wrong one. The depth of the well and the amount of arsenic. Doesn't matter which one I put into which, because right now I'm just looking for a correlation. And boy, that's hard to see, right? Because a lot of them had no arsenic in them, right? And at a variety of depths. So it's kind of hard to see here. Let's actually have SPSS draw a fit line for us, okay, and see what kind of numbers we get. Okay, well look at this. There's an interesting association here. As the depth of the well increases, oh no, I'm sorry. As the, I could have put it the other way around. As the depth of the well decreases, the level of arsenic increases, right? There's an inverse relationship between them. Just to show you that it doesn't make a difference which way I do this for correlation. Okay, and look at the R-square value is 0.06. Is that a strong association, 0.06? Only 6% of the variability in the amount of arsenic is due to the depth of the well. Remember, these are all over different parts of India, these wells, right? So it's not, we know we're not going to get too much useful, actionable information here from the depth of the well, but we at least know now that as we go deeper, we have somewhat more risk of finding arsenic than if we have shallower wells, which kind of makes sense, right? Because the deeper the water is, the more it's been percolating through the various minerals and stuff like that in the ground. Right? So there is some association. How significant it is, we're about to see. Let's go to analyze. Let's go to correlate first. Okay, and I'm going to move two of these in here, depth and arsenic. Now, not all the variables are here. Why are not all the variables here? Because some of the other variables are categorical variables, not numerical variables. If you do correlation, it's only going to bring up the numerical variables. Okay, and the correlation is significant. Look at that value, 0.000, and it's a negative correlation. As one goes up, the other goes down, right? As one goes down, the other goes up, right? So, and it's negative 0.245. Not a great correlation, but it's not due to chance. There is an association between the depth of the well and the amount of arsenic. So let's try our regression, analyze regression, linear. And which one is going to be the independent variable here? Is it going to be depth or arsenic level? Independent variable. Which one causes the other? The depth of the well causes how much, has association, or it causes the variability in the amount of arsenic. At least that's our reasoning. I'm going to click OK. And sure enough, we get a constant value, a slope value, and the slope is negative because as the depth increases, the amount of arsenic goes, as the depth increases, let me think about this. As a depth,
The shallower it is, more.
right? I guess whatever that. I haven't really thought this out, but yeah, whatever the relationship comes out being is what the relationship comes out. The point being is now we have a way to do some prediction, not very great, but we know that there's an association between the depth of the well and the amount of arsenic we expect to find. We can use the formula somewhat predictively, right? But we know it's not going to be such a great prediction because our R square value tells us only 6% of the variability in the amount of arsenic in the water is due to the depth of the well. Other factors influence, how much arsenic is there. Obviously, what kind of mineral deposits there are in the ground, how, if they're up in a mountain, if they're in a valley, and so on and so forth. I'm sure there's a lot of different variables that would account for that. Okay, so there's a few examples of scatterplots, correlation, regression. What kind of variables do we use this for? Numerical. So there are some numerical variables, a handful, maybe 10 numerical variables in your data set, right? Community health survey. There are some numerical variables in there. You can actually sort by the variable type. Actually find the numerical variables. If you think that there's something there you can show an association or that would be meaningful or something like that, you're welcome to go off the reservation and try and maybe alter your topic or something like that. But let me know if you're going to do that, so I can kind of like see where you're going to go with it. Maybe just look over your shoulder for a bit. So at any rate, so I'm gonna close there. We'll pick up on regression again on Wednesday briefly, so we can look at some other forms of regression. There's multiple linear regression. I just mentioned there's other factors that seem to influence this. Well, maybe we can build those factors into our formula and get a better formula. Right? And then there's logistic regression. Like, what if I have a categorical variable and a numerical variable? Can I somehow use this to help me understand whether there's an association or not? Like a yes or no, logistic yes or no, true, false, versus some numerical variable. So we're going to take a quick look at that. We're not going to get crazy with that. We're going to take a quick look at that on Wednesday, and then we'll pick up with, going over the projects and so on and so forth.